Welcome to The Explainer. Today, we're diving into an incredible paper from 1852 by Pafnuty Chebyshev. He took on one of the biggest puzzles in all of mathematics, the mystery of the prime numbers.
So here's the puzzle. It's so simple to ask, but it's mind-bogglingly hard to answer. Where is the next prime number going to show up? For centuries, primes have seemed to just appear, almost at random. It's a chaotic, unpredictable dance that has had the most brilliant minds completely stumped.
I mean, just look at this list of primes up to 50. You see 2, 3, 5, 7, then the gaps get bigger. 11, 13, then a jump to 17, 19. There's no simple, obvious pattern here. And when you can't find a pattern, proving anything concrete about these numbers is just unbelievably difficult.
So people started noticing things, kind of like this idea called Bertrand's postulate. It basically says that if you pick a number A bigger than 3, you're always going to find at least one prime between that number and double it minus 2. Now, this seemed to be true for every single number anyone ever tried, but a hunch isn't a proof. Before Chebyshev, nobody had a way to prove it was always true.
So how in the world did Chebyshev finally crack this thing? Well, here's our game plan. We'll start with the mystery itself. Then we'll look at the brand new toolkit he had to invent. We'll see his incredible master equation, learn how he literally trapped the primes, and finally, watch him solve the puzzle once and for all.
All right, so to tackle a problem this old, Chebyshev knew the existing math just wasn't going to cut it. He had to forge entirely new tools from scratch.
His first invention was this function, data of z. Now don't let the symbols intimidate you. All it does is add up the natural logarithms of all the prime numbers up to a certain value, z. Think of a logarithm as just a way to measure a number's size or weight, so this function gave him a way to measure the total collective weight of all the primes up to a point. Next up, he created psi of x, and this one is even more powerful. It's like theta, but it doesn't just look at primes. It also includes the weight of prime powers, like a prime squared or cubed and so on. This tool gives you a much richer picture of how the primes and their influence are spread out.
And then there's his third tool, t of x, which seems to come completely out of left field. It's based on factorials, 5 times 4 times 3 times 2 times 1. Factorials are about as orderly and predictable as numbers get. So why on earth would he bring this into a fight with the chaotic primes?
Well, this is where Chebyshev's genius really kicks into high gear. He found an absolutely brilliant way to connect these two completely different mathematical worlds. So on one hand, you've got the wild, unpredictable, chaotic world of primes, which he's describing with his psi function. This is the great unknown. And on the other hand, you've got the super neat, structured world of factorials, described by his t function. This part was totally understood. And here it is. This is the master equation. This is the stroke of genius. Chebyshev proved that t of x is exactly equal to psi of x plus psi of x divided by 2 plus psi of x divided by 3 and on and on. He built a perfect, solid bridge connecting the chaos of the primes to the calm order of the factorials. This equation was the key that unlocked everything.
Okay, so now that he has this incredible bridge, what can he do with it? Well, he could do something that had never been done before. He could actually trap the prime functions, putting a fence around them so they had nowhere to hide.
Using some really clever math, he first established a floor. He proved that his prime function, theta of x, could never ever dip below the value of this formula you see here. Now, a is just a constant he calculated, but the main idea is that this whole thing creates a minimum boundary.
And then, you guessed it, he did the exact same thing for the ceiling. He proved that theta of x could also never rise above the value of this other, similar-looking formula. So this is the big takeaway. For the first time ever, the behavior of the primes wasn't a complete mystery. Even though Chebyshev didn't know the exact value of the prime function, he had it trapped. He squeezed it between a lower bound he could calculate and an upper bound he could calculate. He had cornered the primes. With the primes now trapped, Chebyshev could finally unleash this powerful new machinery to attack those long-standing, seemingly impossible problems.
So he went right back to Bertrand's postulate. Using his new floor and ceiling, he could actually calculate the minimum possible number of primes you could find between a and 2a minus 2. And here's the beautiful part. His formulas proved that for any number a over 160, that minimum was always greater than 0. That means there had to be at least one prime in there. For all the smaller numbers, he just checked them by hand. And just like that, a famous conjecture became a proven fact.
But he didn't just stop there. I mean, this new method was like a skeleton key that opened all sorts of doors. In the very same paper, he laid out a clear rule to test if these crazy infinite series with primes would add up to a real number or just shoot off to infinity. He even gave a way to approximate those sums, and this is a big one. He created a formula to estimate how many primes there are below a certain number and was the first person to define exactly what the margin of error was for that guess.
Just to give you an idea of how amazing this was, he looked at an infinite series, adding up fractions like 1/2 log 2, plus 1/3 log 3, and so on for every prime. Before him, nobody even knew if this added up to a finite number. Chebyshev proved that it did, and that the final sum was less than 1.73. That is a stunning level of precision for the 1850s.
Chebyshev's work just completely changed the game. It shows us that even inside the most random-looking systems, there can be a deep, hidden order just waiting to be found. It really makes you wonder, doesn't it? What other simple patterns that we can see in numbers are out there, just waiting for someone to come along and invent the right tools to finally prove them?